Good morning. I'd like to talk some more about multi-step methods today. Previously, we had looked at a situation where we used not only the information at ti, but also at ti minus 1 in order to get an Adams Bashforth method. What we did was we made an interpolation problem where we interpolated not the y values, but the f values. We interpolated at time ti, at ti minus 1. We integrated the resulting polynomial, and the method that we came up with was wi plus 1 is wi plus delta t over 2 times 3 fi wi minus the corresponding f value at ti minus 1 wi minus 1. Shortly, we'll look at the actual program that implements this, which I stored into ab2.f90. We'll also want to compare how good this method is with some of our other methods. As a prelude to that, we'll look again at the Taylor order 2 error versus the Taylor order 3 error to show the scale of things, and then we will compare Taylor 2 with AB2. That sort of method is called excuse me. That sort of method is called an explicit method because it uses only information that's already available. An implicit method uses information that we already know plus some that we don't know, which is a very odd sounding thing. The simplest possible implicit method would be to approximate f by the function value at ti plus 1 wi plus 1. Our approximation would then be wi plus 1 is wi plus the integral from ti to ti plus 1 of the constant value f ti plus 1 wi plus 1 dt, but you can see obviously there's a problem with that, even though in a certain sense the integral is easy to do since this is a constant. If we carry out that integration, we get a very simple looking result, but the problem is that in order to calculate this quantity, we need to know that quantity. On the other hand, if I'm calculating this to obtain wi plus 1, then I already know wi. Delta t is known to me. The procedure f of t and y is known to me, since it's the right-hand side of my differential equation. And ti plus 1 is known to me. In this equation, the only thing that I don't know is wi plus 1. So if I make up an abbreviation, which I'll call x, at each stage, at each step of this differential equation solver, I'm going to have to solve the equation x equals one of the known w values plus delta t times f at ti plus 1 and x. Typically, this is a nonlinear equation and can't be solved in closed form by any simple method. But on the other hand, if you think back to the beginning of the semester, this is a nonlinear equation typically to solve. We have many ways to think about that. We had Newton's method and bisection and the method of false position, and more generally we had fixed point iteration. So one could think of this equation as being x equals g of x, and at this stage, at each stage of the calculation, I have to solve one of these. One idea would be to take a rough approximation to x, feed it into the g function, and hopefully get an improved one, and then repeat this as necessary. This would be fixed point iteration. And if you think back to what we did early in the semester, when does fixed point iteration work out well for us? It works out when the derivative of the g function is less than 1 in absolute value. Again, the g function is a constant plus a constant times f evaluated at, with respect to the fixed point iteration, ti plus 1 will be a constant, x. F generically takes two arguments, t and y. The t slot is occupied by ti plus 1 in this case, and the y slot is occupied by x. The only dependence on g of x is that it appears in the y slot of function f. G prime at x is the derivative of a constant plus a constant factor times, in this sense, the derivative of f is the derivative with respect to that variable. That would be partial derivative of f with respect to y. I have to evaluate that at ti plus 1 and x. Since this is 0, g prime of x is delta t times the partial of f with respect to y, evaluated at ti plus 1 comma x. Suppose that the function f had a continuous partial derivative with respect to y in some closed region that contains the solution. That means, since a continuous function is closed and bounded, that partial derivative must be bounded. Under those circumstances, there's some constant m, so that absolute partial of f with respect to y is no bigger than m. This tells me that the absolute value of g prime, which is equal to that, can't be any bigger than m times the time step delta t. M is a finite constant. If I make delta t small enough, for example, no bigger than 1 over m, then absolute value of g prime at x will be less than 1, and the fixed point iteration will converge to a fixed point of the g function. These x's that I'm calculating will settle down to the wi plus 1 of the Adams-Bashforth method. The Adams-Moulton method, that is. So under those circumstances, these x's will settle down to wi plus 1, and we will have solved the equation that we had, which at first glance appeared to be undoable. Another method that we could look at is I will use the current value of the time and the future value. I'll construct a Newton divided difference table in the way that we have done before, calling the variable of integration u just for convenience. The interpolating polynomial will be given by this quantity, and I'll use this inside the integral to approximate the solution to my differential equation. The integration is direct. This is a constant. That's a constant factor. If u is the variable, then an antiderivative for u minus ti is 1/2 u minus ti squared. When I put u equal to ti, I get 0. Ti plus 1 minus ti is delta t, so I'll get a factor of 1/2 and a factor of delta t squared. you can cancel out a delta t in that last term and obtain this expression, which you could leave written combined or separated as I had before. Wi plus 1 needs to be Wi plus 1/2 delta t f at ti wi plus f at ti plus 1 wi plus 1. And as before, the quantity that we're trying to find shows up over on the right hand side, so we will use a fixed point method or some other method in order to solve that equation. Initially, we'll set W0 equal to the exact solution at T0. We know that number because that's the initial value of the initial value problem. And then for I equals 0, 1, 2, up to n steps minus 1, we're going to solve the above equation, where I'm writing x as an abbreviation for Wi plus 1. We will solve that equation in some way or the other, fixed point or Newton or some other method. Once we've solved that equation, we set Wi plus 1 equal to x and go around and do it again until we've marched all the way across the interval. Lastly, if we want to, we can rewrite this fixed point formula as this right-hand side minus x equals 0. And now we're confronted with the problem of solve this kind of equation, some function of x equals 0. We have a wide variety of ways of thinking about that. One of them is Newton's method. Make an initial estimate of x. X is going to end up being Wi plus 1. So, for instance, if you didn't have any better guess, you could use Wi for your guess. Or you might use the Euler estimate as your rough initial guess. And then we will do a Newton step. X is going to be set equal to what it used to be minus this function that you're trying to make 0, divided by the derivative of this function that you're trying to make 0. We might do a few steps of Newton like this. This above is the function of x that I'm trying to make equal to 0. The derivative of that, for this term, the derivative will be 0 because that's a constant, plus a constant factor, delta x over 2, times, this is a constant because it doesn't have any x in it. We've already talked about what we mean by the derivative of that term. That would be the partial of f with respect to y, evaluated at ti plus 1, comma, the current x estimate that we have, minus the derivative of x with respect to x is 1. So if I decide to go the Newton route, this is going to be done several times. I'll be doing several steps of Newton's method, getting what are hopefully better and better estimates for Wi plus 1, and after I'm done, whatever my x value is will be stored into W number I plus 1. This is the theory part. Next, I want to look at the programming part.